Welcome to The Explainer. Today, we're diving into the story of a force that, well, it does everything. It sparks lightning, it makes your photocopies, and it powers pretty much our entire world. Let's get right into it.
Okay, let's start with a bit of a riddle. What on earth does lightning have in common with a photocopier? I mean, they seem totally unrelated, right? Well, it turns out they both rely on the exact same fundamental force of nature. And to really get our heads around it, we've got to start super small.
All right, so our story really starts with the absolute basics of electricity, electric charge. Everything that's electric comes down to these tiny little properties of matter, and they come in two distinct types, or flavors, if you will, positive and negative. These two are the stars of the show, at least for this first part.
Now, these charges, they play by a really simple but powerful rule. You've probably heard it before. Opposites attract and likes repel. So positive pushes positive away. Negative pushes negative away. But a positive and a negative, they pull right toward each other. This one simple idea, this push and pull, is behind everything. So you might be wondering, how do these charges actually push or pull on each other if they're not even touching? It's a great question. Well, every single charge creates this invisible zone of influence all around itself. Physicists call it an electric field. Think of it like its own personal force field, one that can reach out and affect other charges that enter it.
And even though we can't see it, we can actually map it out. We draw what are called lines of force to visualize this field. These lines are like, well, they're like a little road map showing the exact direction a positive charge would get pushed or pulled. You can see how they radiate out from the positive charge and curve right into the negative one. It's basically a chart of the force itself.
But this map does more than just show direction. It also shows us the strength of the field. And here's the key. Where you see those lines bunching up, packed really tightly together, that's where the force is super strong. And where they're all spread out, the force is much weaker. It's a really clever, really elegant way to see something that's totally invisible.
Okay, so how is this useful? Well, believe it or not, this is exactly how a photocopier works. It's just brilliant, pure applied electrostatics. The machine creates a positively charged drum, then uses light to neutralize parts of it, basically creating an invisible picture out of static electricity. Then, negatively charged black powder, the toner, just sticks to the positive parts left behind, and bam, you've got a copy. So there you go. That's half of our puzzle solved. Okay, so static charges just sitting there, are pretty powerful. But things get really interesting, world-changingly interesting, when those charges stop sitting still and start to flow.
When you get a whole bunch of charges moving together in a coordinated way, that's what we call an electric current. The best way to picture it is like a river. Seriously. But instead of water molecules flowing, it's a massive, steady stream of tiny little charges, usually electrons, all moving through a wire.
So what gets them moving? How do you start the river flowing? Well, you apply that same thing we just talked about, an electric field, across a conductor like a copper wire. That field acts like a constant pressure, giving all the free electrons in the metal this gentle but persistent nudge, forcing them all to drift in the same direction. And that drift, that's the current that powers literally everything you plug into a wall.
Now, for the longest time, for centuries, people thought electricity and magnetism were two totally different things. Electricity was all about static shocks and lightning. Magnetism was about compasses pointing north and weird rocks that stuck to each other. Two separate forces. But then, a surprisingly simple experiment came along and turned that whole idea on its head.
And this is it. This is the moment. A scientist named Ørsted was doing a demonstration, and he just happened to notice that every time he switched on an electric current in a wire, the needle of a compass sitting nearby would twitch and move. There was only one possible explanation for that. The electric current had to be creating its own magnetic field.
This was huge. This was the moment everything changed. A moving electric charge, that's all a current is, creates a magnetic field. Suddenly, they weren't two separate forces anymore. They were two sides of the same coin, deeply, fundamentally connected.
So this discovery immediately leads to a beautiful, logical next question. And the person who asked it was the brilliant Michael Faraday. He thought, okay, wait a second. If a moving charge can create a magnetic field, Can we do it the other way around? Can a magnetic field create a current? Can it make charges move? And the answer was a massive, world-changing yes. Faraday found that by just moving a magnet back and forth near a coil of wire, a current would just appear in the wire, out of nowhere. No battery, no power source, just motion and magnetism. He called it electromagnetic induction.
But here's the crucial part, the detail that makes all the difference. A magnet just sitting next to the wire, it does absolutely nothing. Faraday's law makes it clear. The magic happens because of change. It's the changing magnetic field that induces the current. You have to keep that magnet moving or the current just stops. It's all about change.
So we have this beautiful symmetry, right? Moving electricity makes magnetism, and moving magnetism makes electricity. This perfect little dance isn't just a cool fact for a physics book. It's everything. It's the reason our lights are on right now.
And you can see this perfect symmetry in two devices you use every day, the electric motor and the electric generator. They're literally opposites. A motor pumps electricity in to get motion out. A generator uses motion in to get electricity out. One converts electricity energy to motion, the other converts motion right back into electrical energy. It's the same principle, just running in reverse. And the magic of induction doesn't stop there. It's also the secret behind transformers, those big gray boxes you see on power poles. They use a changing magnetic field from one coil to induce a totally new current in a second coil. This lets us crank the voltage way up to send power over long distances without losing much energy, and then step it way back down so it's safe to use in our houses. Without transformers, our entire power grid just wouldn't work.
So think about the journey we just took. We started with one single, tiny charge, just sitting there, pushing or pulling on its neighbors. We followed it as it started to move, creating a current. That led us to its hidden twin, magnetism. And putting those two together revealed this incredible, interconnected force that, and this is no exaggeration, literally powers modern civilization.
But there's one last twist to the story, one final mind-blowing piece of the puzzle. Remember that dance? A changing electric field creates a changing magnetic field, which then creates a new changing electric field, and so on and so on. What happens when that dance becomes self-sustaining and starts flying through space? You get a wave, an electromagnetic wave. And you know these waves very well. They are radio waves, they're microwaves, they're X-rays, and they're every single color of light that you can see. But how that works? Well, that's a story for another explainer.